While NASA's websites flicker offline and earthly telescopes are blinded by the sun, the third confirmed interstellar object, 3I Atlas, speeds past Mars at 30 million kilometers per hour. This is the highest cosmic irony. While this strange traveler, glowing with emerald light, approaches us, America's scientific sources shut down. Only the orbital spacecraft of Mars, from Europe to China and the United Arab Emirates, can take advantage of this moment and capture what Earth cannot see, obtaining the clearest images and data before the Tri-Eye, Atlas, disappears forever. But what can the Martian probes discover under the pressure of the situation? This object breaks all the rules about comets. The time of the encounter with this alien is already upon us. On October 3rd, 2025, the geometry of the solar system will prevent Earth from participating in the observations. When the 3I Atlas flies past Mars at a distance of only 0.2 astronomical units, about 30 million kilometers, the Sun is directly between us and the comet. From the Earth's perspective, the angle of elongation, the part of the sky separating the Sun from the three stars, decreases to 10 degrees. For ground-based telescopes, this means a complete stop. Most observatories do not risk their optics or sensors when an object is less than 15 degrees from the sun. By early October, the comet's position falls directly into this dangerous zone for 6 weeks, from the end of September to early November. However, Mars is on an orbit with a deviation of more than 40 degrees. The angle between the Sun, 3AI, Atlas, and Mars on October 3rd is wide, often exceeding 50 degrees. This means that Martian orbital and ground devices have a clear, unobstructed view, while all eyes on Earth are blinded by sunlight. The numbers tell this story. At the moment of closest approach, the view of Earth is blocked, but Mars is at the forefront. Any changes, eruptions, or anomalies in the behavior of the Tri-Eye, Atlas during this period will be recorded primarily or only by machines that hover or crawl across the red planet. In this brief moment, Mars becomes the only observation tower of the solar system. Every lost hour now means a permanent gap in the records. The window for observation from Mars is not measured in weeks or even days. It's just a few orbits, a tiny segment of time before the comet drifts away and the geometry changes again. Mission planners, usually working to meticulously crafted schedules months in advance, are forced to improvise. Standard protocols are postponed for emergency redirection. Instruments meant for scanning Martian valleys or analyzing the thin atmosphere are suddenly aimed at deep space. Data transmission channels, calibrated for slow routine science, are forced to handle streams of raw telemetry and fast images in hopes of catching any eruption or anomaly before they vanish. The pressure does not relent. Every passage overhead, every opportunity to transmit data could be the last chance to capture a new detail or sudden surge. There is no time for bureaucracy or doubts. Everything depends on the speed and flexibility of the teams working behind these remote machines. Mars is under the watch of several spacecraft, each designed to study a specific spectrum of electromagnetic waves and under its own mission team. European Space Agency's Mars Express and ExoMars Trace Gas Orbiter provided high-frequency observations for a week starting from October 3rd. Mars Express uses a high-resolution stereo camera and the Amiga spectrometer to capture multispectral images and analyze chemical signatures in the visible and infrared ranges. The Nomad and ACS spectrometers of the Trace Gas Orbiter break the light of the comet into thousands of wavelengths, searching for rare gases and molecular bands. Both devices can pivot away from Mars to track the comet, but each maneuver requires balancing thermal and safety constraints. Initial data may appear within a few days, but full public releases are usually published only months after calibration and validation. The Hope orbiter of the United Arab Emirates offers a different approach. His camera ASH and ultraviolet spectrometer EMU, usually focused on studying the atmosphere, can be reconfigured to monitor bright objects in the Martian sky. The global orbit of Hope and its flexibility in targeting make it suitable for wide-angle shooting and ultraviolet spectrum, especially if the scientific team approves a rapid response campaign. In past events related to comets and solar storms, Hope provided processed data for a week if the results required it. The Chinese Tianwen-1 spacecraft, equipped with high and medium resolution cameras and a mineral spectrometer, could provide contextual images and near-infrared spectra if reconfigured. although official confirmation of the Three Eyes campaign is still awaited. Data from Tianwen-1 is usually made available to the public through curated releases or scientific articles, sometimes weeks or months after collection. The NASA Mars Reconnaissance spacecraft, equipped with a high-resolution camera and the CRISM spectrometer, has experience in campaigns studying comets and asteroids. Deviations from planned objectives depend on pre-approved plans and the safety of the spacecraft. The current shutdown of the U.S. government complicates public access to new data, even though the MRO is collecting it. Internal teams continue to monitor the status of the device and planetary protection. In addition to Mars, the European Space Agency's JUICE spacecraft will attempt to observe the Three Eyes comet during its flyby in November. The geometry is less favorable, and its instruments, such as genres, marges, and UVS, are designed to study distant faint objects. Any data collected by JUICE will face a long queue for transmission, and public release is not expected until early 2026. Even a few spectra or images could help track the comet's activity as it passes around the sun. This network forms a multi-layered approach, where each mission contributes a unique perspective and spectral range. Some results may come within a few days, others only after months of validation. Staged releases and coordinated actions of various agencies ensure the gradual unveiling of the story about a three-eyed slice of the atlas, with each dataset potentially serving as a clue. 9 minutes. That is how long the rover Perseverance continuously observed the Martian sky on October 2nd. Each frame captured by the cameras on the right mast has an exact timestamp in coordinated universal time and embedded metadata: exposure time, filter, camera orientation. The sequence was designed for astronomical observations, but this time, a streak appears. She crosses star trails, not aligning with known satellites and not matching the slow movement of planets. The first step is calibration. Raw images go through a special algorithm, adjusted for even lighting, dark pixels subtracted, defects corrected. Every artifact, every cosmic radiation, every ghostly reflection must be detected and excluded. The camera calibration process is familiar to the team. They need to compare the sky background, check brightness units, and align the frames. Only then does a stripe begin to stand out, a weak, rapidly moving line that is constant in each exposure. Next, the astronomical service is connected. Analysts use SPICE cores, a NASA geometric tool, to translate the rover's orientation into celestial coordinates. The presumed path of the three-eyed slice of the atlas, obtained from the horizons of Emeritus, overlays a stack of images. The angle and speed of the streak are measured, nearly 400 angular seconds per second, corresponding to the expected movement of the comet as seen from the Jezero crater at that hour. The direction is correct, the speed is also right, but a match is not confirmation. False positives must be excluded. Cosmic rays usually leave sharp traces on a single pixel, not long continuous lines across several frames. Internal reflections and ghostly effects repeat with camera movement, but this strip remains stable. Median filters and sigma clipping are applied to remove temporal artifacts. Each candidate is measured by the flow of light, checked for signs of flickering or dimming that could reveal camera malfunctions or Martian dust. The next stage is photometry. The strip is faint but persistent. Her brightness, measured along its entire length, corresponds to what a blurred, rapidly moving comet might produce at a distance from Mars. The light curve is smooth, without spikes or sharp declines. Analysts compare this to comet ejection models and solar reflections, finding nothing unusual. The final test is conformity. The strip's position is plotted on the chart of expected ephemerides for the three-eyed slice of the atlas. The deviations, the difference between expected and observed data, fit within a few arc seconds, which is well within the acceptable margin of error at this distance. Evidence accumulates, but official confirmation remains elusive. The government crisis in the U.S. leaves leading JPL specialists unable to speak out. Their review is on hold. Independent analysts like Simon Schmooze and Shem House publish their findings, but the verification chain awaits NASA's approval. The stakes are high. If this trace truly exists, it will be the first direct observation of an interstellar object from the surface of another planet. But science demands rigor. Every step, calibration, astrometry, photometry, and false alarm checks must withstand scrutiny. While the Muscom Z team from Arizona State University and the Jet Propulsion Laboratory remain silent, the community holds its breath. A trace is captured, frozen in 9 minutes of Martian sky. Whether this event will be an important discovery or a warning depends on what happens next. On September 25th, a single amateur observatory in Namibia captured what would soon become the last clear portrait of the three-eyed comet known as Atlas before the window to Earth closed. An image taken under the southern sky just hours before the comet vanished behind the solar conjunction captured an emerald comet stretching nearly 700,000 kilometers, almost twice the distance from Earth to the Moon. Its core glowed with a green color, distinguishing it from most comets in the solar system. Sunlight filtering through a cloud of dicarbon and other gases scattered in a way that created a bright, almost unnatural hue. But the structure of the comet was even stranger. Instead of a long tail of dust, typical in astronomy textbooks, Atlas displayed an anti-tail directed towards the sun rather than away from it. This feature, shaped by large, slowly moving particles, and the unusual geometry of its interstellar path gave the comet an appearance more like a drifting fan than a classic tail. Weaker shells and arcs spread from the core, indicating layers or episodes of ejection rather than a stable flow. Subsequent images from September 27th and October 2nd, though noisier and shadowed, confirmed this pattern. The boundaries of the coma maintained their shape, even as the object dimmed, resisting the smudging and elongation expected from a typical dusty tail. Each new frame heightened the feeling that this was not an ordinary comet, but something acting by its own rules, a guest with an internal logic. These images, collected in the last days before the forced darkening of the Earth, now serve as a starting point for everything Mars will see next time. The numbers related to Comet Atlas do not match any known pattern. Let's start with the speed. Most long-period comets enter the solar system at speeds of 20 or 30 kilometers per second. This object does not slow down. It flies past Mars at nearly 60 kilometers per second, and by the time it reaches perihelion at the end of October, models predict its speed will increase to 68 kilometers per second. This is a speed that leaves even the fastest comets of the solar system in the dust. The trajectory is also strange. Instead of crashing into the solar system at a steep angle, Comet Atlas follows along the ecliptic, its tilt barely deviating a few degrees from the plane of the planets. For a true interstellar visitor, this is a statistically rare phenomenon. Most comets are expected to appear from high orbits, not slip almost unnoticed through the solar system. The next mystery is size. Initial brightness estimates, combined with coma models, indicate the presence of a core at least 5 kilometers in diameter, possibly even larger. This makes it one of the largest interstellar objects ever observed, comparable in size to two comets, I/Borisov, and significantly exceeding Oumuamua. But the coma itself is even more intricate. Instead of a classic dust tail stretching from the sun, there is a vast multi-layered shell. Polarization studies hint at concentric shells or arcs, each reflecting light differently. There is no long fibrous tail here, only a massive structured cloud that contradicts the usual physical laws of comets. Polarimetry and visualization only confirm the anomaly. The green color of the coma, caused by diatomic carbon, stands out against the others, but its stability is also noticeable. Despite solar heating and interaction with a coronal mass ejection, its morphology changes little. The parameters, speed, tilt, size, and structure of the coma form a profile that does not fit the usual cometary frameworks. For dynamic modelers, each new observation presents a fresh challenge, and traditional methods do not provide clear answers. On September 25th, Comet 3 Atlas collided with another body, a coronal mass ejection shot directly from the sun. Space weather forecasters tracked a CME as it moved into interplanetary space, predicting a surge of charged particles and magnetic fluctuations. For most comets, such a solar eruption is a recipe for chaos. The sudden influx of energetic plasma can strip ions from the coma, trigger rapid gas release, and form new tails in just a few hours. Scientists in plasma laboratories and solar observatories expected a standard reaction: a shockwave, a burst of ionized gas, perhaps even a visible bend in the comet's shell. But reality proved more restrained. When the CME enveloped the 3I/Atlas, ground telescopes and instruments on the Mars side tracked the aftermath. Instead of a dramatic outburst or altered coma, the structure of the comet barely changed. The green halo remained sharp, the anti-tail held its wedge shape, and the outer shells showed no signs of sudden expansion or fragmentation. The morphological changes were minimal. There was no obvious ion tail, no sharp increase in brightness, and not even ripples in the layered arcs of the coma. For plasma physicists, this became a mystery. More ionization was expected, a swollen envelope, or at least a hint of magnetic oscillations in the light of the comet. The lack of a strong reaction leaves open questions about the object's composition and internal structure. Is the coma extraordinarily stable, Or is there something in its chemistry that makes it resistant to sunlight? Without a clear ion tail or emission line burst, traditional diagnostic tools prove ineffective. Researchers are now turning to plasma science tools in orbit around Mars and high-frame spectra in search of clues, hoping that somewhere in the raw telemetry data lie traces of a solar storm waiting to be discovered. The orbit of 3I/Atlas leaves no doubt about its origin. Its trajectory passes through the solar system on a hyperbolic path, unbound by gravity and not meant for return, which is a mathematical imprint of interstellar travel. This fact places him in rare company, alongside only two previous guests, one I/Oumuamua and two I/Borisov. But confidence in his origin is just the starting point. The real issue is how to name him and how much trust can be placed in these labels. Some researchers choose the familiar term interstellar comet, referring to the green comet, gas outflows, and layered shell. Others hesitate, pointing to the lack of a dust tail, an anti-tail, a persistently stable structure, and a high, almost mechanical speed. The debates concern not only terminology, but also evidence and criteria for unusual claims. Science moves forward through skepticism, questioning not only what fits, but also what will withstand the next round of data. The lessons of one I/Oumuamua are still fresh. Models multiply, speculations rush forward, but only hard numbers remain. For 3I/Atlas, every anomaly, every strange color, every shell, and every unblinking coma must be checked, not advertised. The question is not whether it can be created, but whether any dimension compels this step. Until then, the only certainty remains his interstellar passport. Everything else is a hypothesis waiting for the next spectrum, the next image, the next surprise. For all who observe the history of the 3I/Atlases, the most important tools are open data streams and community analysis.